Hello, welcome back to the wonderful world of physics. This is the beginning of chapter 25 on electric circuits. And in this video, we'll look at the first two sections, section 1 on circuits, symbols, and electromotive force. And then section 2, looking at resistors aligned in both series and parallel. We'll start with some common circuit symbols. And as we go through learning about electric circuits, these are symbols you'll see. In the top is some of the more common symbols. So you see the symbol of a resistor and a capacitor. Now you'll note the symbol for a capacitor, it reminds us of the parallel plates, that structure that we've seen in previous lessons. We have a source of electromotive force. So think of that as a battery or a cell. Notice how it's drawn with parallel lines, and there's a large line and a short line. And in this particular picture, it's long, short, although it can also be drawn just with a simple long and short. But the long side always represents the positive terminal, and the short side is the negative. We can also have a voltmeter, a switch, and down below we can see an ammeter. That's something that measures current. A variable resistor, so you see it's the resistor symbol with an arrow through it, a variable capacitor, ground, and also a fuse. So some of these symbols we'll be seeing later on as we study circuits. Now, in an electric circuit, when we think of a wire, most materials, even metals that are good conductors, have some resistivity, they have some resistance. But for the short distances that we'll generally be thinking about circuits, effectively we'll take them as being perfect conductors, meaning while they do actually have a non-zero resistance, it's going to be so small we're going to take it as negligible. So we're going to take our wires in our circuits, assume them to be zero resistance. To maintain a current, we need a device such as a battery to maintain a fixed voltage. Which leads to an electric field in the conductor. So we need a source of what's called electromotive force, EMF. So we call it EMF, although you should know that this is not a Newtonian force as measured in newtons, but it's just something that keeps the current going. It provides that fixed electric potential. And it'll be something that converts some other form of energy, for example, chemical energy, to electrical energy by separating the charges. So some examples are a battery. You see in the lower left hand, there's a car battery. A battery turns chemical energy through chemical reactions into electrical energy. Here on the right, you have a generator. A generator turns mechanical energy into electrical energy. There can also be photovoltaic cells, which turn light into electrical energy. And then biologically, there are cell membranes which control the ion flow in and out of cells. For our purposes in this chapter, we'll mostly be thinking about a battery. So let's talk about this electromotive force, or EMF. Here's the analogy. Here is what a battery does, and let's use, as I often do, a gravitational analogy. We have this ramp right here, and this person lifts up a ball. So the mass that the person is lifting up is analogous to electrical charge. And the gravitational field is analogous to the electric field. So this person is basically representing the battery. She is lifting up the mass against the gravitational field. So that's what a battery does. It lifts charges against the electric field. It says here, lifting against gravity represents the energy conversion process in an EMF. And then she lets the ball go down, and it says the charge falls through an external circuit, dissipating energy in collisions. So the ball falls down, and we're going to think of that as going through resistance until eventually the ball completes the circuit and it comes all the way back to the person where the person can lift it again. So the idea with an electric circuit is that first you have the battery that effectively lifts the charge against the electric field. And then the current is going to go from positive to negative, falling through resistances as it goes, and eventually it ends up right where it started. It says here the battery is the source of EMF, and the EMF drives the current through the resistor. Electromotive force, or EMF, is work per charge. So it's measured in volts, you already know that, and think of it as a volt is a joule per coulomb. And so it refers to the work in lifting a charge against an electric field. The assumption that we're going to use is that, as I mentioned before, wires are perfect conductors, meaning zero resistance, so that the voltage across a resistor, if you only have one resistor, is the battery's EMF. Here we have Ohm's law. Now you've seen it before as current equals voltage over resistance, but now we're going to replace that V with this script E, and that's the EMF. So the current, if it goes through one resistor, is going to be the EMF divided by the resistance. I use a script E here because I don't want to use capital E, normal capital E, because we already use that for electric field. And in other physics applications, we already use E for energy. So capital E is getting kind of overused. So we'll use a script E, mostly so we don't confuse it with electric field. Here is the got it question. Section 25.1 at the end of the section. It says the figure shows three circuits which are electrically equivalent. So while they all look different to each other, electrically, two of them are equivalent to each other. So if you look at circuit A, you can trace what the current is doing. It goes through a circuit. As it goes through the circuit, it goes through a resistor. At that point, the current will divide up. It'll go down and it'll go to the right. So it'll divide up between these two resistors that are actually in parallel to each other. Then the current will join up again at this lower junction and continue on to the battery. So what we've got is a circuit that has resistors. There is one that's in series with these two that are in parallel. So I've written that in shorthand as series plus two that are in parallel. Now let's look at this second one. The current, we start at the positive voltage, and remember that's always when we have long, short, we'll start with the long, that's positive terminal, so that's where the positive current will start, and it'll go around the circuit, it'll go through a resistor, and then it will go through these two that are in parallel to each other. So the two that are in parallel, they are in series with this one. So I've written that out as, again, you have series plus two parallel, which just means that the first one is in series with two parallels. It's equivalent to the first circuit. Now let's look at the third one. Here we have the current. We start at the positive terminal. It goes, and now it meets a junction. So it's different from the other two. The other two, it hit a resistor first, but it's meeting a junction. And you've got these two limbs, these two legs that are parallel to each other. Some of the current will go down, some of it will go to the right. And as it goes to the right, there are these two that are in series with each other. So and then it continues on, then they join up again at this lower junction and continue. So here we can say that this resistor on the left is in parallel with these two that are in series with each other. So I've written that as it's in parallel with the two that are in series. So we can see that circuits A and B are electrically equivalent to each other, and they are different from circuit C. Now we'll further explore the idea of resistors in series and parallel. In a previous chapter, you learned about capacitors in series and parallel, and so now we'll talk about resistors. Let's first talk about when resistors are in series. When they're in series, that is defined as that all the current that goes through resistor 1 must also go through resistor 2. Here we have a schematic diagram. We're going to trace the current, and we always trace going from positive terminal and around to the negative terminal. So it goes from the positive terminal through R1 and then through R2, and there's no deviating from that path. All of the current that went through R1 had to also go through R2, so they're in series with each other. Here is more my illustration. I've got a battery right here, and the current going through the first resistor, then the second resistor. What that means is that the current through resistor 1 is equal to the current through resistor 2. And it's like water going through pipes. All the water, all the gallons per second that went through pipe 1, the pipe segment 1, also goes through pipe segment 2. Now there must be some electric potential. It says must be some electric potential V1 across R1 to drive the current through that resistor. If you look at my picture here, kind of like the picture I showed earlier in this video about the person lifting up the ball and then dropping it, think of the total battery. What the battery's EMF is climbing a huge ladder. So we think of it as the battery lifts it up so many volts. Well, we can think of going up so many meters. And then you drop the ball, you let it slide. Well, resistance in this analogy is going down some distance. It's think of it as there's a drop in voltage. So the wire has no resistance, but then the ball goes down this amount. Now with the ladder and a ball, we can think it goes down so many meters. But with the electric circuit analogy, we can think it drops so many volts going through R1. And then the wire where it doesn't drop any, and then it drops so many volts again. When it gets to the bottom, it's dropped as much voltage as the EMF raised it up. Just like with the ladder analogy, you went up so many meters, and then through the course of the ball, how it goes, it drops that many more meters to get right back where it started. So we can say using Ohm's law that the voltage drop across resistor 1, V1 is the current times R1. Also, V2 is the current times R2. Now, just as you can see with the ladder analogy here, the electromotive force of the battery is the sum of those, V1 plus V2. And if there were a third resistor, it would be plus V3. So then substituting in the IR expressions, we can say that the electromotive force of the battery is IR1 plus IR2. Before you let this page go on to the next one, make sure you understand what I've said so far. Pause it if you need to. Okay, so at the top of the page is where I left off, that the electromotive force of the battery is I times R1 plus I times R2. Now, if we think about what the total current is through the battery, ignoring the individual resistors, Ohm's law says the total current is the electromotive force of the battery, as measured in volts, divided by the equivalent resistance. We could say the total resistance of the circuit. Here I've labeled it as the resistance of the series. Now, let's make this substitution. Electromotive force is IR1 plus IR2. We're still dividing by resistance of the series. Let's take this equation and divide it by I. Sorry that my I, or the font I looks just like my 1. We're dividing by I, and we get 1 equals R1 plus R2 divided by R of the series. Finally, algebraically multiply both sides of the equation by R of the series, and here's our important equation that I've just derived, that the total effective resistance of a bunch of resistors in series is simply the addition of those resistances. So the total effective resistance when resistors are in series is R1 plus R2 plus as many resistors as you have. Now we could then look at what is the voltage drop across each resistor, and we're going to use Ohm's law, putting it together with what we've learned so far. Well, if we want to know the voltage drop across resistor 1, Ohm's law says V1 equals IR1, and we know that I, the current, is, and let's come back up here, current is the electromotive force of the battery divided by the total resistance of the whole series. So it's electromotive force over resistor series. We're still multiplying by R1. And now I'm going to substitute in the series resistance is R1 plus R2. That's what it says in this box right here. So in the end, we get that the voltage drop across resistor 1 is this expression, R1 over R1 plus R2 times the electromotive force. Now, following the same reasoning, the voltage drop across 2, I've taken it through the algebra, but you can just trade out 1 and 2, and now we have R2 over R1 plus R2 times the voltage. But taking it through the math, it's the current times R2, which is electromotive force over series resistance times R2, and here we have that expression. So as the current goes first through one resistor, then through the other resistor, there is a voltage drop in each resistor, and the battery's voltage is divided in proportion to each resistor. So let's say it's a 9-volt battery. Depending on the resistances, there might be a voltage drop through one resistor of 6 volts, and the voltage drop through the other one is going to be 3 volts, and that's going to depend on their resistances. Let's do an example in the book, example 25.1. It says a light bulb with resistance 5 ohms is designed to operate at a current of 600 milliamperes. To operate this lamp from a 12-volt battery, what resistance should you put in series with it? You see in my picture, as well as the corresponding picture that's in the book, even though I've been using the word resistor, we could also more generally talk about any appliance, anything, any gizmo that has resistance to it. So while I've drawn this bulb as a resistor, that's fine. We're looking for its resistance, and we want to know what is R1 given R2 is 5 ohms, given that the electromotive force is 12 volts. And we're also given what the current is through R2, which is the light bulb. Well, we can start by thinking of Ohm's law, I equals V over R. Let's call that R equals V over I. And so the series resistance has to be 12 volts divided by 0.600 amperes, because it's 0.600 amperes that goes all the way through the circuit. And so we know that the total resistance has to be 20 ohms. Now, if R2 is 5 ohms, then R1 must be the thing that'll complete the 20 ohms. So it has to be 15 ohms. Now, we could also ask, what is the voltage over each resistor? What is the voltage drop? Now, we know that they add to 12 volts, and they are divided in proportion to the resistances. So we can use the formulas that I gave on the previous screen, that V1 is R1 over R1 plus R2 times the electromotive force, 15 ohms divided by 20 ohms, times 12 volts, and that gives 3/4 of the total voltage drop. 3/4 times 12 volts, and that's 9 volts. Whereas the 5 ohm resistor, use the same expression, V2 is 5 ohms over 20 ohms, times 12 volts, which is 1/4 of 12 volts, which is 3 volts. So you can see here in this example how the voltage drops are divided. The 15 ohm resistor versus the 5 ohm resistor gets more of the voltage drop in proportion to those voltages. It is 3 times more resistant. It has 3 times more resistance than R2, and so it's got 3 times the voltage drop. Make sure that you study and understand this example because the concepts in this example are very fundamental to your understanding of circuits and more complex circuits that will be coming up soon. Let's look at the Got It question 25-2. It says rank from highest to lowest the voltages across the identical resistors R at the top of each circuit shown and give the actual voltage for each. It says in A, picture A, the second resistor has the same resistance R, and in B, the gap is an open circuit, meaning infinite resistance. All right, so let's first think about A. You've got 6 volts and you've got these 2 identical resistors. And again, the question is to think about and actually rank from highest to lowest the voltage across the identical resistors R. Well, in picture A, we've got that the voltage is going to be the one resistance of the one resistor divided by the total resistance. So we have R over 2R. And then we're multiplying by 6 volts, so we get 3 volts. So each resistor being identical in picture A is going to get half of the voltage drop. The battery lifts it up by 6 volts, then it goes through the resistor and it drops by 3, and then it drops by another 3. Let's look at picture B. We have the resistor, but notice there's a gap right here of infinite resistance. So no circuit is actually, no current is going to flow because there isn't a closed circuit. So here we get voltage equals R over the total resistance is infinite times 6 volts. So there is 0 voltage drop across that resistor. In fact, there's no current at all that runs. And then in picture C, we've got 6 volts and we see there's only one resistor. And without doing the math, we can see that all of the resistance drop has to happen through that one resistor. So it's got to be 6 volts. Now, if we did the math, I didn't even write out the math here, but using the equation, let's go back to what I wrote for A. We could say R over the series resistance, which is R. So it's 1 times 6 volts, and that gives us 6 volts. So ranking them in order from highest to lowest, it would be C, A, and then B. I want to look for just a little bit at the idea of a real battery. It's not an ideal electromotive force because it has internal resistance due to resistance in the materials, due to limitations in the rate the chemical reactions can separate the charges. What we do is we model a real battery as an ideal EMF in series with an internal resistance. So when we think about a battery, here I've got in green the battery with the positive and negative charge, but we're going to mathematically model it as it's an ideal EMF with a little internal resistance. We're just going to pretend that inside that battery is a battery with a resistor in series with it. And then as we leave that battery, then we have the what we'll call the external load, whatever resistor, light bulb, whatever we have hooked into the circuit. Now, if the internal resistance is much, much less, if it's negligible compared to the external load, then we can say the voltage drop across the load is, and using the formula that we've used a couple of times already, the resistance of the load divided by the resistance of the entire series circuit. But remember, now we're imagining that there's an internal resistor inside that battery. So the denominator has the sum of those resistances. And if that internal resistance is negligible, then the voltage drop across the external load is simply the voltage of the battery. Now, if 2 times, for example, 2 times the internal resistance is the resistance, the external load's resistance, so that's a pretty significant internal resistance, we can run that formula and we get the voltage across the load is R load over R load plus R internal times electromotive force, and it becomes 2/3 times the electromotive force. And that is pretty significant, that it's not simply the electromotive force, but rather based on some internal resistance in the battery, the voltage drop is only 2/3, which means for a 9-volt battery, you only get 6 volts across the load. We've been looking at resistors in series. Now let's look at what happens when we put resistors in parallel. Remember from chapter 23 when we studied capacitors in parallel that the voltage across circuit elements in parallel is the same. That's also true for resistors. So for example, we have this diagram. Here we have R1 and R2. They are parallel to each other. And you can see how visually you can see that they're parallel by, you imagine the current going through and it hits a junction. And some current divides into R1, some current divides into R2, and eventually they join up again. That's parallel. Less visually is the idea that R1 and R2 have the same voltage drop between them. Now, these resistors have a common voltage, electromotive force, and we can say I1, the current that goes through 1, as you can see in the diagram here, is electromotive force over R1. And I2 is electromotive force over R2. Let's look at the junction that I've labeled A. The total current, I've labeled right here as I, is I1 plus I2. So many coulombs per second go into junction A. And those coulombs per second are going to be divided. Some of them are going to go through I1, some are going to go through I2. They'll eventually meet up again. So at this junction down here, it'll eventually become the full I, the full current. But as they divide up, we can see that I equals I1 plus I2. We'll use Ohm's law and say I equals electromotive force over R1 plus electromotive force over R2. Now we're going to take this equation, and in the next line I'm going to factor out EMF, and I'm also going to divide both sides of the equation by EMF. So we get I over EMF equals 1 over R1 plus 1 over R2. By Ohm's law, I over the EMF is the total resistance that is in the parallel circuit. And so what we have is, it is 1 over the total resistance, because Ohm's law says that resistance is voltage over I. So this is 1 over resistance. What this means is, and here we have in the box the important equation that I've just derived, the important equation that you'll need to use, that there's a reciprocal sum relationship with the resistors in parallel. 1 over the total parallel resistance is equal to 1 over R1 plus 1 over R2, and if there are more resistors, you add those reciprocals. I want you to notice that when you have a parallel combination of resistors, the resistance of that combination, the total parallel resistance, is always less than the lowest resistance in the combination. So if we find ourselves wanting to build a circuit, and let's say we need 20 ohms in our circuit, 20 ohm resistance, but all we have is a bunch of 100 ohms. We don't have anything as low as 20. We can actually add the 100 ohm resistors in parallel in a certain way so that it will overall come out to a smaller resistance. And we can in fact add a bunch of hundreds, actually 5 of them in parallel will make a 20 ohm resistor. There's an analogy to traffic on the road. When you imagine you have congested traffic, there's a lot of what we could call resistance. But if you open up extra lanes, it eases the traffic congestion. There's less resistance. So you can think just like adding resistors, you would think that would add more resistance. But in the traffic lane analogy, every lane has its own resistance. Opening up another lane doesn't add more resistance. It actually takes away from the overall resistance, and you ease up the traffic flow. Well, quick little example here. Let's say we have one resistor that's 100 ohms, another one that's 200 ohms. We put them in parallel with each other. And so 1 over the total resistance is 1 over 100 plus 1 over 200. And that's 3 over 200. Then we have to take the reciprocal of that to get the parallel resistance. We get 66.7 ohms. And notice again that it is less than either of the individual resistors. Do this one by yourself. This next one, see that you got the answer that I get. You take 100 ohms and 5,000 ohms, put them in parallel with each other, and you should get 98 ohms. Again, take a minute to do that by yourself. Make sure you get the answer that I got. Up at the top of the screen, just a handy little reference here. When you have parallel resistors or series capacitors, they add reciprocally. So you can go back to chapter 23 and see how we covered capacitors in series and parallel, but they add reciprocally if they are parallel resistors or series capacitors. They add normally, meaning you just add R1 plus R2 plus R3 if it's resistors in series or capacitors in parallel. So they're reversed between resistors and capacitors. All right. Let's look now at the got it question. 25.3. It says the figure shows all 4 possible combinations of 3 identical resistors. Rank them in order of highest to lowest resistance. Highest to lowest resistance. So all of them are resistance R. You look at the first one, and it's 3 all in series with each other. The second one is 3 in parallel with each other. The third is a parallel combination. First you've got R, and it's in parallel with those 2 R's. Now I've already started to solve the problem, you can see right there, because I want you to think of, in picture C, these two, this leg of the parallel is actually 2 resistors that are in series with each other. So you can think of them as a single resistor that is 2R. And picture D has the 2 in parallel, and they together are in series with the one down below. So we can think about picture A, resistors that are simply in series, you just add them up, R plus R plus R, and that's 3R. The second one is resistors all in parallel. So we'll say 1 over R plus 1 over R plus 1 over R is 3 over R. Remember, then you have to take the reciprocal of that because all that's given us is 1 over the total resistance, but we have 1/3 R. So you can see by putting them in parallel, it's much lower resistance than picture A when they were in series. But now let's look at these series parallel combinations. We have a parallel of, first on the left is a resistor R, and then on the right, we're going to lump those two together since they're in series, R plus R as 2R. So we put together the parallel combination, it's 1 over R plus 1 over 2R. Well, going through the math, we get 3 over 2R. Take the reciprocal, and it's 2/3 R. Picture D. First, we need to consider what is this parallel combination. Then once we find what it is, we'll put it in series with the one down below. So let's look at the parallel first. 1 over RP is 1 over R plus 1 over R, which is 2 over R, which means the total effective parallel resistance for this bit that I've circled here is 1/2 R. Now we're going to put it in series with the R down below. So the series resistance, which then is the resistance of the entire picture, is the R parallel plus the R down below, which is 1/2 R plus R, and then 3/2 R. So now we can look at all these and we can rank them in order from highest to lowest. So the highest being A, which is 3R, and then D, 3/2, and then C, 2/3, and then B, 1/3 R. Let's look at an example. There's a battery, there's 4 resistors, as you can see on the circuit, and I've given them resistances of 100 ohms, 150, 200, and 200. And what I want to do is calculate the total effective resistance. Make sure that when you come away from this video, you understand this example right here, because it's a good example that'll help you to understand all the different ways that we analyze these relatively simple circuits. What I'm going to do, I usually start as far away from the battery as possible. Not always, but what I'm going to do is identify the series and the parallel combinations. Remember when you do this, that components are in parallel only if they're connected directly together at each end. Components are in series only if the current through one component has no place to go but through the next component. And so the first thing we can do is recognize that R1 and R2 are in series, and they are in series with this parallel bit right here. First thing we should do is see if we can turn this parallel bit into an equivalent resistance. So let's see what the resistance of 3 and 4 together is. I'm going to call it the resistance of 3/4 because what I'm going to do is, using some imagination, I'm going to figure out what their effective resistance is just of 3 and 4, and I'm going to imagine pulling those resistors out of the circuit and replacing them with a single resistor. And I'm going to call that resistor R34. Using the parallel resistor formula, the reciprocal of R34 is the reciprocal of R3 plus the reciprocal of R4. So it's 200 to the -1 plus 200 to the -1, which is 0.010 over ohms. Take the reciprocal of that, so R34 is 100 ohms. Now when I turn the page, I'm going to have redrawn this circuit, and I'm going to have imagine replacing these two resistors with a single resistor that I'm going to call R34. Here we go. All right, there it is. And here I've written it down that R34 is 100 ohms. Now, we have a series combination. And we're not going to worry about the parallel, the separate 3 and 4 again, as we're figuring out the total resistance. Now we just have these 3 in series. R1, R2, and R34 are in series with each other. So the effective resistance is, and we're going to add those 3 series resistors, 100 ohms plus 150 ohms plus 100 ohms. That gives us 350 ohms. So that's the total effective resistance. In the book, there is on page 424, Tactics, Analyzing Circuits with Series and Parallel Components. And it takes you through the different steps, and I advise you to refer to that, but I've basically taken you through those different steps. And then it continues on. Perhaps you might want to solve for the voltage drop across each resistor, and it gives you some good steps to follow. Let's do an example, and I'm going to follow those tactics, but again, that page is there for you to review as necessary. Let me just take you through the steps. Example 25.3 says, find the current through the 2 ohm resistor in the circuit. Well, in order to find the current through any of these, we have to get an idea of what the whole current is. And that starts with figuring out what the total effective resistance is. And ultimately, we want to know the current through this 2 ohm resistor. So we're going to break this down and find the total effective resistance. Well, what I see is that these two, the 2 ohm and the 4 ohm, are in parallel with each other. We'll use the parallel resistor formula that I have here in the green, and I've labeled these resistor 1, resistor 2, resistor 3, and resistor 4. So the resistor, what I'll call 2, 4, we're going to add the reciprocals of resistor 2 and resistor 4, 1 over 2 ohms plus 1 over 4 ohms. And when we add those and take the reciprocal, we should get resistor 2, 4 is 4/3 of an ohm. Now we are imagining replacing those two resistors with a single resistor, and now we see these three are in series. 1 ohm and 4/3 ohms and 3 ohms, so the total resistance of the entire circuit is 5.33 ohms. If we want to know the total current, notice this picture that I've drawn. I've redrawn the circuit. I've imagined that all of those resistors are just one resistor all by itself. And so we have a 12-volt battery, a single 5.33 ohm resistor. So the entire current, you can think the current that's drawn from the battery is 12 volts over 5.33 ohms, so 2.25 amperes. Okay, now, tactic step 5, you can refer in the book, so that it says work backward, replacing series and parallel equivalents with combinations of individual components. At each point, apply Ohm's law to find the currents through and or the voltages across the individual components. All right, so we're going to do that. We're going to work backwards and redraw the diagram. So here we have the series bits. Now, remember that when you have resistors in series, they carry the same current as their series equivalent. So that 2.25 amperes runs through each of these series resistors. And because ultimately we are going for what is the current in the 2 ohm resistor, we're really concerned particularly about what's going on in this branch right here, that resistor 2, 4, because it's going to include resistor 2. So we recognize that 2.25 amps runs through each of these resistors. And now we're going to focus on the 2.25 amps that runs through this resistor 2, 3. Now let's continue to redraw the original diagram. We're going to separate out this 4/3 ohms back into its original 2 ohms and 4 ohms. And as we are working our way backwards, we also want to remember that parallel components have the same voltage as their parallel equivalent, meaning whatever the voltage drop we imagined through this 4/3 ohm, that's the voltage drop between both the 2 ohm and the 4 ohm. And here I've drawn, just to remind us, the ladder analogy. It's as if you have two ramps that are next to each other. They drop the same amount. Those are parallel resistors. They drop the same amount, meaning they have the same voltage drop. So we can say that that voltage drop, what is it? Well, using Ohm's law, it's the current. We've already established what the current is up here, times the resistance, that equivalent resistance, and so 2.25 amperes times 4/3 ohms is 3 volts. So 3 volts is the voltage drop through both the 2 ohm resistor and the 4 ohm resistor. And now we're going to finish up by using Ohm's law to figure out, now that we know the voltage drop across the 2 ohm resistor, what is the current through it? So current is V2 over R2. It's a 3 volt drop. Divide by 2 volts, and we get 1.5 amperes. By the way, just so you can see how this more plays out, the current through resistor 4, this 4 ohm resistor, is 3 volts divided by 4 ohms, which is 0.75 amperes. And you notice that they add up to 2.25 amperes. Now, if you look at my red marker, you see the current, the total current in the battery we established at the top of the page was 2.25 amperes. And as it hits this junction, some of it divides up. 1.5 amperes goes through resistor 2. 0.75 amperes goes through resistor 4. It decided how much to send through which based on the resistances. So the 2 ohm resistor, it's got half the resistance and it got twice the current. You've probably heard the expression that electricity takes the path of least resistance. And that's not exactly true. There's some truth to that. But if it was true that it takes the path of least resistance, then it would have all gone through the 2 ohm resistor and ignored the 4 ohm. Rather, what happens is it takes the path, it divides up, and it gives greater proportion of current to the least resistance. So again, as you can see in this problem, if something got, like the 4 ohm, if it's twice the resistance, then it only got half the current going through it. That is the end of section 25.2. Have a great day.